Hi, in this video I am discussing a question on lateral deflection of a light ray when it passing through a glass cuboid. The question is shown on the screen. Okay, a glass cuboid is kept in air, so you know the opposite sides are parallel. So light is entering from the upper surface, the angle of incidence is I. Since the opposite sides are parallel to each other, the emerging the light ray which is emerging into air will be parallel to the light ray entering into the glass cuboid. So even they are parallel to each other, there is a deflection. Light would have gone this way if there is no glass cuboid. But finally, the light is emerging into air along this path. But that is parallel to the initial direction of the light ray. But there is a deflection. This deflection is called lateral deflection. In this question, it is denoted by X. The thickness of the glass cuboid is T, and the refractive index of the material of the glass, or the refractive index of the glass, is N, that is the absolute refractive index. The glass cube is surrounded by air. We can take the refractive index of air almost equal to 1. So we need to show that the lateral deflection X is given by this relationship, where I is the angle of incidence in the upper surface, N is the refractive index of the glass cuboid, and T is the thickness of the glass. We need to derive this one. Okay, so we can show this is the angle of incidence. You know, angle of incidence and angle of refraction are always measured with the normal to the boundary. Then only we can use the Snell's law, sin I over sin R equal refractive index. Only when we can use that only when I and R are measured with the normal to the boundary. So this is angle of incidence. So this is the normal. So I can say this is the angle of refraction R. This is the angle of refraction R. Okay, so I'll extend this line here further and it touches the bottom edge of the glass cuboid. This is the lateral deflection X. I'll draw a line parallel to this one from this point. So I can name this point P. This point I can name it P. So from P, I'm going to draw a line perpendicular to the initial direction of light ray. So that will be equal to X, that length will be equal to X. So this is X and this is 90 degree. So if I say this is Q, I'll name this one Q, this one Q. So the length QP, I name it as L. Okay, so in the triangle, this I'll name it as N. So in the right angle triangle, PQN, we know that this is angle of incidence I. So this is whole thing is I. This is R means this angle will be equal to I minus R. I minus R. This angle, because opposite angle. So with the normal, this is I. The whole thing is I. This is angle of refraction R. So the angle PQN will be I minus R. So in the triangle PQN, I can say L sine I minus R is equal to X. So that means X equal L sine I minus R. This could be written as L, you know, sine I minus R is equal to sine I cos R minus cos I sine R. So I can write this will be L sine I cos R minus cos I sin R. Okay, so sin I and cos I are related to I, which is given in the question. Only thing I need to get some expression or relationships for cos R and sin R. Okay, so now I know that in this triangle, when you consider the triangle PQL, I'll name this one L. In the triangle PQL, in the triangle PQL, it's a right angle triangle. This is 90 degree. I extended the normal. So in the right angle triangle PQL, I know that L cos R is equal to T, the thickness of the glass cuboid. So I can say L equal T over cos R. So I can replace this L by T over cos R. So I'll write X equal, instead of L, I can say T over cos R into sin I cos R minus cosine sin R. Okay, multiply cos R inside the bracket. T cos R will get cancelled. So sin I minus cos I into sin R over cos R. Okay, so sometimes friends thinks we can't we replace this by tan R. Yes, you can replace it tan R. Then you have to follow another path in trigonometry. You had to use, tan r. Then we had to say sec squared r equal 1 plus tan square r. We need to find the sec squared r. That is, sec r equal to 1 over cos r. We can go that way also, but I am not going to follow that method. I am going to find sin r and cos r separately. Okay, so I can say the upper boundary. For the upper bound, I can say n is equal to sin I over sin r. Sin I over sin r for this wave at the upper boundary. So sin r is equal to sin I over n. So sin squared r, I'm going to square it because I want to get. So sin r, I got it here. So I can say this as equation 1. This is equation 2. So I got sin r in terms of sin I and n. Sin I and n are the given quantities. So I can replace this sin r by this expression. Only thing I need a cos r. How can I find the cos r? Sin squared r plus cos squared r equal to 1. So I'm going to use that relationship. So I'm going to square it. Sin squared r equal sin squared I over n squared. Sin squared r I can write 1 minus cos squared r equal to sin squared I over n squared. So from this, you can get cos squared r. So cos squared r, make the cos squared r subject, 1 minus sin squared I over n squared, that I can write n squared minus sin squared I over n squared. Take square root on both sides. Cos r equal square root of n squared minus sin squared I over n. Let it be third equation. Right, now I found everything. I found cos r, I can replace it here. Sin r, replace it here. You will get the final answer when you solve it by substituting 2 and 3 in equation 1. Okay, use the equation 1. So you can say x equal, equation 1 and x equal t sin I minus cos I sin r. Sin r you can replace sin I over n divided by cos r. Replace this one, square root of n squared minus sin squared I over n. Okay, now what will happen? This n and this n will get cancelled. Sin I, they are common. I can take the sin I out. So this n and this n will get cancelled. Here sin I, here also sin I. I can take the sin I common. So t sin I, this will become 1 minus sin I, took it out, cos I over square root of n squared minus sin squared I. That's the final answer. They asked to derive it. Okay, simple is it.